In the last part of chapter 16, we're going to look at the relationship between planes and lines and multiple planes. So, the big question is, how do we find the angle between a line and a plane? Where we're going to start is how we would find the angle of intersection between the normal to the plane, this here, and the line. We have a direction vector, we have a normal. Well, we've been working with a formula for a little while now that allows us to deal with that. Cosine of theta, where theta would be the angle in between them, the acute angle, is equal to the absolute value of their dot product over their magnitudes. So, how does the angle between the plane and the line relate? So how do we find this angle down here? Maybe call it phi. Well, if we envision a right triangle here, we're dealing with a normal, we're dealing with the direction vector, opposite hypotenuse. This is also equal to the sine of phi. So this formula that we have here, n dot d over magnitude of d, magnitude of n, is equal to the cosine of theta, or the sine of phi, the sine of the angle between the line and the plane. So here's two lines. We want to, here's a plane, here's a line. We want to find the angle between them. Well, we saw that in rectangular form, we can look at the coefficients to determine the normal of that plane. The normal of this plane is going to be 1, 2, negative 1. We can take our line and write a direction vector for it. 1, negative 1, 2. Now to find phi, we're going to do the absolute value of n dot d. So 1 minus 2 minus 2 over the two magnitudes. So the magnitude of d, the magnitude of our direction vector, would be 1 plus 1 plus 4, or 6. Magnitude of our second direction vector will also be the square root of 6. So what we have is the sine of phi equals this stuff. We can simplify this stuff so that phi is the inverse sine of 3 over 6, and that's equal to 30 degrees. If we want the angle between two planes, so we don't have a line and a plane, but we have two planes, plane 1 and plane 2, and we're looking for theta down here. Each of these have a normal, n1 and n2. So perpendicular there. This angle right here is going to be 180 minus theta, and by default that would make this angle up here theta, and since these two are vertical angles, that is also theta. So to find the angle between two planes, we can simply find the angle between two normal vectors. So theta is going to be the inverse cosine of n1 dot n2 divided by the magnitude of n1 times the magnitude of n2. Now to do an example. We have two planes. We want the angle in between them. N1, if we call this plane 1, is going to be 1, 1, negative 1. If we call this plane 2, N2 is going to be 2, negative 1, 3. So theta, the angle in between these two planes, will be the inverse cosine of 2 over the square root of 42, which is approximately 72 degrees. Make sure you can get these. The top number, absolute value of the dot product. And on the bottom, we have the magnitudes being multiplied together. Now we have three planes, and I want to use row operations to solve this, to find the intersection, essentially. But we don't just have x, y's, and z's. We've got this other parameter m. So let's set up our augmented matrix. And for our first reduction, what we're going to do is we're going to take row 2 and replace it with row 2 minus 3 row 1. And row 3 will be replaced with row 3 minus row 1. Why don't you do those two operations and then start the video again to make sure that you've done it correctly. We've got 1, 3, negative 1, 0. Second row becomes 0, negative 4, 2, 0. And row 3 becomes 0, negative 8, 3 minus m, 9 minus m squared. Now we're going to take and do row 2, and we're going to replace that with negative 1/2 times row 2. Just to make things a little bit smaller and to get the leading coefficient to become positive. Notice both of those can be divided by 2. We're going to take row 3 and replace that with row 3 minus 2 row 2. So again, pause the video, do this reduction, and then restart it. And here's what we end up with. And it says in the directions to interpret our results. Well, what we could say is that if m equals negative 1, what we end up with in the last row is 0 equals 8. And we have no solutions then. Second possibility would be if m doesn't equal negative 1, if it equals something else, then z would equal m squared minus 9 over m plus 1. And you might be asking, well, how do we get that? Well, we take this last row. I can factor a negative out of the two terms. That's times z equals 9 minus m squared. Divide both sides. Z is equal to negative m squared minus 9. I can factor a negative out of there also. and the negatives would cancel each other out. Now we can advance up the matrix up to the second row, and we get that y is equal to 1/2 z. We can manipulate this row, we can rearrange things, and so what we end up with is 9 minus m squared over 2 times m plus 1. For the last part of this, take the first row, and I'd like you to find an expression in terms of m for x. So what you should have come up with is that x is equal to negative 3y plus z. We have an expression for y, we have an expression for z, so x can be written of the form negative 3m squared minus 9 over 2 times m plus 1 plus m squared minus 9 over m plus 1. And may as well get a common denominator here. And then we can distribute and combine some like terms on top. We get 9 minus m squared over 2 times m plus 1. So in ordered triple, we could write down as the intersection point of these three planes would be 9 minus m squared over 2 times m plus 1, comma, 9 minus m squared over 2 times m plus 1. And lastly, our z would be and I have things written backwards here, don't I? This should be m squared minus 9. Z is m squared minus 9 over m plus 1. So there is our ordered triple for the intersection of these planes, provided that m doesn't equal -1, because in that case there is no solution.